Welcome back to the Deep Dive. Today we are really getting into the weeds with a critical document. We're starting our mission into ACI 31825, the building code requirements for structural concrete.
And we're kicking off right at the beginning, Chapter 1, General.
Exactly. This chapter, it might seem basic, but it's the absolute foundation. We're talking about the essential roadmap for all concrete engineering, really.
It absolutely is. And it's crucial to understand this isn't just like background reading. Chapter 1 lays out the legal framework. It's about compliance, safety, how projects actually get executed.
Right.
And a key thing we need to establish up front is the difference between the code itself, that's the mandatory requirements, and the commentary, which is, the explanation or the background info. Very different roles.
Okay, good point. So our mission today, looking at Section 1.1 scope, is to sort of unpack the 9 main areas Chapter 1 covers.
Yep.
We've got the general requirements, the code's purpose, its applicability, like where does it even count? How to interpret the language, the roles of the key players, the building official and the licensed design professional.
Critical roles.
Then documentation, testing, and inspection rules. And finally, how you get approval for, special systems, the new stuff.
That covers the map, and we should probably nail down the reference right away. Section 1.2 calls ACI 318 the code throughout.
It's simple enough.
And it specifies the official version is English, using inch-pound units. Now, Committee 318 does develop SI and Spanish translations.
Which is helpful.
Very helpful. But Section 1.2.4 is the legal fine print, if there's ever a conflict between versions.
Let me guess, the official English one wins.
The official English inch-pound version governs. Always.
Yeah.
That's the benchmark for compliance disputes.
Okay, that makes sense. Establishes a clear hierarchy, especially if you're working internationally or with metric plans. You need to know the ultimate reference point.
Precisely.
All right, so let's dive into the core philosophy then. What's the fundamental purpose behind this whole document? Sections 1.3 and 1.2.7 seem key here.
Section 1.3, purpose. Yeah, this is really the heart of it. The code exists, it says, to set out the minimum requirements needed for public health and safety.
Okay, health and safety.
And also for durability, serviceability, and the overall structural integrity of concrete structures. It's a broad mandate.
That word again, minimum, that feels like the most loaded word in this whole chapter.
It really is.
If ACI 318 is the minimum for safety, what does that mean for the licensed design professional, the LDP? Can they just meet the minimum and call it a day or ignore it?
Ignore it, absolutely not. The code is the floor. It's the baseline you cannot go below. Our 1.2.5 reinforces this. These are the minimum standards. But, and this is crucial, the LDP absolutely has the ability and often the professional responsibility to specify requirements that exceed those minimums.
Ah, okay. So the code sets the floor, but the engineer can build higher, so to speak.
Exactly. It's often necessary for the project's specific needs.
Can you give an example? When would just meeting the minimum be, technically okay, but maybe not the right engineering call?
Sure. Think about maybe a tall building in an area with low or moderate seismic activity. The code's minimum seismic detailing might be fairly light.
Right, because the perceived risk is lower.
But maybe the client is, say, a tech company with super sensitive equipment on the upper floors. They need minimal vibration. Or perhaps the owner wants the building to last 100 years, not the sort of standard 50-year design life that often underlies the minimum.
Gotcha. So the code's minimum handles basic safety for standard assumptions, but it might not cover specific performance goals like low vibration or extreme longevity.
Precisely. In those cases, the engineer must exceed the code minimums. Maybe they specify a much lower water-cement ratio for that 100-year durability goal, or thicker concrete cover over the steel than the absolute minimum required.
To prevent corrosion over that longer lifespan.
Exactly. That's where the real engineering judgment and value comes in, strategically exceeding the minimums based on project needs, not just blindly following the baseline.
That clarifies the professional obligation nicely. Now, speaking of boundaries, Section 1.3 also seems really important for what it says the code doesn't cover. This sounds like lawyer territory.
Oh, it definitely is. Sections 1.3.2 and 1.3.3 are huge for risk management. 1.3.2 says the code doesn't cover design considerations beyond the minimums for safety and serviceability.
Meaning, if the code doesn't demand a higher standard, the engineer isn't legally obligated by this code to provide it, though they might choose to.
Correct. And then, even more critically, 1.3.3 states the code explicitly does not address construction means, methods, techniques, sequences, or procedures, unless, of course, a specific requirement is stated elsewhere in the code itself.
Okay, let's unpack that means and methods exclusion. That sounds like a major point of friction on job sites. Where's the line between a design requirement, which is the engineer's responsibility, and a construction method, which is the contractor's?
It's a classic distinction. Think about a concrete wall. The code the design specifies the wall needs a certain strength, say 5 inches to $4,000 PSI, and a certain amount of rebar. That's the what?
The final product specs.
Right. But how the contractor achieves that, the type of formwork they use, the shoring system designed to hold it up, the order they pour the concrete lifts in, the specific mix slump they choose to make it pumpable. Those are all means and methods.
So if the contractor's temporary shoring fails during the pour and the wall form blows out,
the liability generally falls on the contractor because the shoring design and installation was their chosen method to achieve the engineer's specified result.
okay. The engineer is responsible for the final structure being adequate according to the design strength. The contractor is responsible for the process and temporary works to get there.
Exactly. The only time the code might step into means and methods is if a particular method is essential to achieve the final required structural performance, like maybe specific vibration requirements for placing mass concrete, or placement rules for self-consolidating concrete to avoid segregation.
Got it. That's a very clear line for liability. Okay, let's shift gears slightly. How does ACI 318, which is very specific to concrete, fit into the bigger picture of building regulations, like the general building code?
Good question. Section 1.2.7 addresses that. ACI 318 is usually an adopted standard. It's part of a larger legal framework.
It's not the only rulebook on site.
Definitely not. So if ACI 318 doesn't provide a minimum requirement for something within its scope, maybe a specific material test or design aspect or strength evaluation, then you default back to the requirements of the general building code for that jurisdiction. ACI 318 handles the concrete structure, the general code handles everything else, like fire ratings, exits, plumbing, etc.
So it's specialized, but it has to work with the general code, which naturally leads to potential conflicts. What happens if different documents seem to say different things?
Chapter 1 sets up a clear hierarchy for resolving conflicts. We already hit 1.2.4 official English inch-pound version trumps translations. Then there's the code versus commentary relationship. Section 1.5.3 is explicit. The commentary, the R sections, provides background and intent, but it's not binding.
So you can't use a sentence from the commentary to argue against a clear requirement in the main code section.
Nope. The code provision is the law. The commentary is like the explanatory notes or legislative history. Helpful for understanding, but not enforceable on its own. It cannot be used to create a conflict where the code is clear.
Okay, that's a crucial distinction for enforcement officials. What about conflicts with other documents that ACI 318 might reference, like an ASTM standard for rebar?
Section 1.5.8 covers that. If there's a conflict between a provision in ACI 318 and a standard or document it references, the ACI 318 provision governs.
So ACI 318 maintains its authority within its domain.
Exactly. It ensures that overall concrete design philosophy remains consistent. For instance, ACI 318 might have specific minimum cover requirements for rebar durability. If a referenced ASTM standard somehow implied a different tolerance that violated that minimum, the ACI 318 minimum requirement prevails because it's the governing structural code adopted for the project.
All right, that hierarchy makes sense. Let's move on to section 1.4 then, applicability. Where does the code actually apply? And maybe just as important, where does it not apply? Because those exclusions can trip people up.
Definitely. Section 1.4.1 starts simple. The code applies to concrete structures designed and built under the general building code. Pretty broad.
Okay.
But the commentary, R1.4.3, gets more specific about structures that ACI 318 should be used for, even if they aren't typical buildings. These are often complex, specialized structures.
Like what?
Things like concrete arches, storage bins, silos, blast-resistant structures, even nuclear shielding walls.
Right, the really high consequence stuff. Why single those out?
Because they deal with loads and conditions way beyond normal building design. Silos have unique pressures from flowing materials, right? That's covered in ACI 313. Nuclear structures need to handle heat, radiation, specific safety factors, that's ACI 349. Large tanks have hydrostatic pressure issues, ACI 350, or ASME codes for containment.
So ACI 318 provides the basic concrete principles.
But Chapter 1 immediately flags these special cases and points the engineer towards the specific ACI or other codes needed for those unique mechanics. It acts like a switchboard, directing you to the specialist standard.
Okay, that's helpful guidance. What about existing structures? That's a huge part of the work engineers do today. Renovations, repairs.
Section 1.4.2 addresses that. It says ACI 318 can be used for assessment, repair, and rehab of existing structures. However,
There's always a however.
it must be used in conjunction with ACI 562. That's the specific code for existing concrete structures.
Why the two codes?
Well, ACI 318 gives you the rules for designing new concrete material properties, strength calculations based on current standards. ACI 562 gives you the framework for evaluating what's already there, how to assess its current capacity, deal with degradation, figure out compatible repair strategies. You can't just apply today's new construction rules directly to a 50-year-old building without the assessment context of 562.
Makes sense. You need both the target standard and the method for evaluating the existing condition. Okay, let's get into those hardline exclusions now. The areas where ACI 318 says, nope, not me, starting with residential.
Right, section 1.4.6. This excludes typical small residential buildings, 1- and 2-family houses, townhouses, and their accessory structures like garages.
Why exclude them? Concrete foundations are common there.
The thinking is that these structures usually follow simpler, often prescriptive building methods found in residential codes, not requiring the full complexity of ACI 318 analysis.
So for a standard house foundation, I probably don't need to run full ACI 318 calculations.
Generally, no, unless the local jurisdiction specifically adopts ACI 332, which is the residential code requirements for structural concrete. ACI 318 is basically saying we're for bigger engineered structures, but if you want ACI level rigor for a house, use 332, which is tailored for that scale.
Okay, now a very specific one.
It's
Deep foundations. Section 1.4.7 mentions an exclusion based on size.
Yes, it excludes deep foundation members, think piles or drilled shafts, if their lateral dimension or diameter is less than 10 inches.
10 inches. Why that specific number seems a bit arbitrary.
It's not entirely arbitrary. The commentary, R1.4.7, explains that below this 10-inch threshold, the behavior of these slender elements tends to be dominated more by geotechnical factors, soil interaction, friction, and bearing, rather than the internal concrete stresses, like flexure and shear, that ACI 318 is primarily focused on for larger structural members.
So for things like micropiles or very small diameter piers, the geotechnical design standards become more critical than the detailed concrete structural checks in 318.
That's generally the idea. It distinguishes between predominantly geotechnical elements and predominantly structural concrete elements based on that dimension.
Interesting distinction. Okay, next exclusion. Slabs on ground. Section 1.4.8. That covers a massive amount of concrete poured.
Huge amount. But ACI 318 doesn't apply to them unless the slab is doing more than just sitting there.
Doing more how?
If the slab is transmitting vertical loads from columns or walls down to the soil, or if it's acting as a structural diaphragm to transfer lateral forces like wind or seismic shear from the building above to the foundation system.
So if it's part of the building's load path for gravity or lateral forces, it counts as structural, and 318 applies.
Exactly. But if it's just a basic floor slab in a warehouse poured directly on prepared grade, it usually falls under guidance from other ACI documents like ACI 360 for design or ACI 302 for floor construction, which focus more on flatness, durability, and jointing.
Got it. The moment it helps hold the building up or keep it stable, 318 kicks in. What about newer materials? Fiber reinforced polymer, FRP bars.
Section 1.4.9 explicitly excludes members reinforced only with FRP bars.
Why the exclusion? FRP is used in structural applications.
It is, but ACI 318's entire safety philosophy, especially around failure modes, is built on the predictable, ductile yielding behavior of steel reinforcement. Steel stretches significantly before it breaks, giving warning.
Right, ductility.
FRP, being non-metallic, behaves differently. It's generally linear elastic right up to failure, which tends to be brittle, sudden fracture. Its fundamental mechanics don't align with the core assumptions built into ACI 318's equations and safety factors, which rely on that steel yielding.
But people do use FRP, so where do they go?
The code doesn't leave you hanging. R1.4.9 immediately points you to ACI 440.11, which is the specific guide for designing concrete structures reinforced with FRP bars.
Okay, so it excludes it but provides the correct reference. The commentary also mentions hybrid members.
Yes, that's where it gets complex. A hybrid member might use both traditional steel rebar, designed under ACI 318, and FRP reinforcement, designed following ACI 440 principles.
How does that work?
The key design challenge, and what ACI 318 implicitly protects by its exclusion, is ensuring that the steel component still meets all its requirements under 318. You want to make sure the ductile steel governs the behavior, providing warning before failure rather than having the brittle FRP snap first unexpectedly. Designing these hybrids needs careful consideration of strain compatibility and failure modes across both material types.
That sounds like a tricky design integration problem.
Oh.
Okay. Another specific exclusion, tanks and reservoirs, section 1.4.10.
Right. Liquid retaining structures are excluded. Their primary design driver is often very strict crack control and deflection limits to prevent leakage.
Makes sense. You don't want your water tank leaking.
Exactly. And ACI 318's minimum requirements for things like crack width control might not be stringent enough for water tightness, especially under constant hydrostatic pressure or fill and emptying cycles. They need specialized design rules.
So where do engineers find those rules?
The exclusion points directly to the relevant codes. ACI 350 for environmental engineering concrete structures, and potentially ACI PRC 334.1 or PRC 372 for specific tank types. If it holds liquid, you need those specialized durability and crack control provisions.
Okay, one more applicability point. Composite steel deck slabs. Very common in floors.
Yes, sections 1.4.5 and 1.4.11 handle this. There are two cases. If the steel deck is just acting as a permanent formwork, a stay-in-place non-composite deck, 1.4.5, then ACI 318 treats the concrete slab on top just like any other reinforced concrete slab.
Simple enough. But what if it's composite?
If it's a composite deck slab, 1.4.11, meaning the steel deck itself is designed to act together with the concrete, usually serving as the positive moment reinforcement.
Like the bottom reinforcement in the middle of the span.
Exactly. In that case, ACI 318 only applies to the concrete portion when it's acting as conventionally reinforced concrete, typically for negative moments over supports or for shear checks. The composite behavior, how the steel deck and concrete work together, is governed by standards from the Steel Deck Institute, or SDI.
So, Chapter 1 again clarifies which standard governs which part of a combined system.
Precisely. It defines the jurisdictional boundaries between different industry standards.
Okay, that covers applicability and exclusions quite thoroughly. Let's shift now to the procedural side and the people involved. Section 1.5 deals with interpretation.
Right. This section is about the language itself, how to read the code.
And it seems very strict. Section 1.5.6 lays out the key words. Shall means it's absolutely mandatory, no choice.
Correct. Shall is a requirement.
Should is advisory, it's a recommendation. Good practice, but if you don't follow it, you probably need a good reason, though it's not a direct violation like ignoring a shall.
Exactly. It implies strong guidance but allows for justified deviation.
And may is permissive. It just means you're allowed to do something, but you don't have to.
Optional. This language, shall, should, may, is fundamental to how codes are written and enforced. Legal interpretations often hinge on these words.
And what if you hit a technical term that isn't defined right there in the section?
Our 1.5.5 sends you to the official source, ACI Concrete Terminology, or CT. You don't just grab a standard dictionary, you use ACI specific technical definitions to maintain precision.
Okay, language defined. Now, who uses and enforces this language? Sections 1.6 and 1.7 talk about the building official and the licensed design professional.
Yep, the key players. The building official, or BO, defined in Chapter 2, is the authority who enforces the code within a given jurisdiction.
The local inspector, basically.
Often, yes, or the head of the building department. But Section 1.6.2 puts a limit on their power regarding ACI 318 itself. While they enforce it, they can't just change the ACI requirements on a whim. They apply the adopted standard as written.
They're the referee, not a player changing the rules mid-game.
Good analogy. And they have important powers under 1.6.3, like ordering tests on materials. If they suspect something isn't up to spec, they can demand proof of quality.
Okay. And the other side of that coin is the licensed design professional, the LDP, also defined in Chapter 2, Section 1.7.
This is the engineer or architect of record. The individual who is ultimately responsible for the structural design and its adequacy. They stamp the drawings.
The buck stops with them for the design.
It does, but projects are complex. So Section 1.7.1.2 allows the LDP to delegate portions of the design work.
Delegate? Like what?
Common examples are things like the detailed engineering for precast concrete connections, specialized anchorage design, or the detailed calculations and shop drawings for post-tensioning systems. These often go to specialty engineers working for the supplier or contractor.
Okay, but if the LDP delegates the post-tensioning design and something goes wrong with it, who's ultimately responsible? Can the LDP say, not my fault, I delegated that?
No. Our 1.7.1.2 is very clear on this. Delegation is allowed, but the ultimate responsibility for the structural adequacy of the entire system remains with the delegating LDP.
So they have to review the delegated work.
Absolutely. They must review it for compatibility with their overall design, check the assumptions, ensure the boundary conditions match, and confirm it integrates correctly and safely into the main structure. If a delegated PT beam design causes problems for the column it rests on, the LDP who approved that integrated system is still on the hook. Responsibility for the overall structure cannot be fully transferred through delegation.
That's a critical point about professional responsibility. Okay, so the LDP designs it, or oversees delegated design. How is this design communicated and recorded? Section 1.8, construction documents.
Section 1.8.1 requires the LDP to prepare drawings and specs that meet the local jurisdiction's rules and, importantly, the requirements laid out in Chapter 26 of ACI 318.
Chapter 26 sounds important then.
It's huge. Chapter 26 basically lists everything that needs to be shown on the drawings: concrete strengths, rebar sizes and grades, cover dimensions, specific detailing for seismic zones, load information, you name it. It's the checklist for complete documentation.
And we live in a digital age. How does the code handle computer analysis? Section 1.8.2.
It allows it, of course. Engineering relies on software. But it puts strict requirements in place to avoid the black box problem, where nobody can tell how the software got the answer.
So you can't just submit the final numbers from your program.
Definitely not. R 1.8.2 demands enough documentation of the input, the output, and the underlying assumptions, so that a reviewer like the building official or a peer reviewer can actually verify the analysis.
What kind of specifics are needed for that verification?
You need to show the input data, material properties, acetal-doles, the loads applied, the support conditions, boundary conditions. You have to state the design assumptions the software used. And crucially, some form of validation is often expected, maybe comparing results for a simple part of the structure to hand calculations, or showing the software meets certain benchmarks.
In the output.
The output needs to be clear too. R 1.8.2 mentions things like identifying members clearly, showing the applied loads, spans, and then the key results: shears, moments, reactions, deflections at critical locations. Enough detail for someone else to follow the structural logic and check the numbers.
So transparency is key, even with complex software. Okay, design documented, now we build it. Section 1.9, testing and inspection.
Right. This section basically points again to Chapter 26 and the General Building Code. It mandates that testing of materials like concrete cylinder breaks, rebar tensile tests, and inspection during construction must be performed, and the records kept.
This is the quality control check during construction.
Exactly. It's the proof that what was actually built matches the quality and strength specified in the LDP's design documents that the BO approved. It closes the loop.
Okay, last section in this group, 1.10, approval of special systems. What if you invent a totally new concrete anchor or have a novel construction method not covered by the code?
ACI 318 needs a way to allow innovation without compromising safety. Section 1.0 provides that path.
How does it work?
Section 1.011 says any system, material, or construction method not already covered needs to be backed up by solid evidence analysis or test data. You have to prove it meets the code's fundamental requirements for strength, serviceability, durability, etc. Just saying it works isn't enough.
Data-driven justification.
Right. And then, according to R 1.10.1, the approval usually involves a review by some kind of expert body, maybe a board of examiners appointed by the building official, or recognized competent engineers. They review the data and analysis to confirm the new system truly meets the intent of the code.
And if they approve it,
once approved, the rules established for that specific new system carry the same weight and enforceability as the rest of ACI 318 for that project. It's a formal process to incorporate vetted innovation.
okay, that covers the procedural framework. So we've got the purpose, the applicability, the language, the players, the documentation, and innovation. That's a lot for just Chapter 1.
It really sets the entire stage. You can't properly apply any of the later chapters without understanding these ground rules.
Absolutely. Now, before we can even think about calculating a shear force or designing reinforcement in later chapters, we need the language of calculation itself. That seems to take us briefly into Chapter 2, notation and terminology.
Exactly. If Chapter 1 sets the rules of the game, Chapter 2 defines the vocabulary and symbols we use to play it. Section 2.1 says its scope is notation and terminology. Section 2.2 starts the list.
And this isn't just a casual glossary, is it? The precision seems intense.
Oh, it has to be. In structural engineering, every single symbol, every subscript means something very specific. If you mix them up, your calculations are wrong, potentially dangerously wrong.
Let's look at a few examples from the outline. We mentioned earlier, the depth of the equivalent rectangular stress block.
Right. That single letter A represents a core concept in flexural design Whitney's stress block. It simplifies the complex reality of concrete stress distribution under bending into a mathematically manageable rectangle for calculating the internal compression force. Using A for anything else in that context breaks the calculation.
Okay. And you mentioned the difference between gross area ALRs and the confined core area.
Yes. AHO is just the total cross-sectional area. Think of the full outline of a column. HO is the area inside the perimeter defined by the ties or spirals, the part of the concrete that's effectively confined by the transverse reinforcement.
And why is that HO important?
It's critical for column and wall design, especially under high compression or seismic loads. The code equations for things like shear strength in columns or the enhanced strength and ductility of confined concrete rely specifically on areas that's actually getting help from the ties, not just the gross area.
Yeah.
Using the wrong area gives you the wrong capacity.
Got it. Subtle but critical. What about reinforcement areas? We had AS versus ASHO.
Another precise distinction. ASHO specifically means the area of non-press longitudinal steel, your standard rebar. ASHO is the total area of longitudinal reinforcement, which includes both HO, the rebar, and ASHO, the area of any pre-stressing steel in the section.
So if you have a pre-stressed beam, you need to be careful which A you're using in different equations.
Absolutely. Using AS when the equation calls for ASA or vice versa will lead to incorrect calculations of strength or maybe minimum reinforcement requirements.
Okay, let's bring in a really fundamental concept for safety.
Yeah.
The strength reduction factor, 5.
Yes.
VSLA.
VSA is bobbing fully in Chapter 21, but used throughout the code. This factor is applied to the calculated nominal strength, the theoretical strength based on material properties, to get the design strength.
Why reduce the strength?
It accounts for unavoidable uncertainties. Materials maybe aren't quite as strong as specified, dimensions might be slightly off, construction quality varies. It's a core part of the load and resistance factor design, LRFD safety philosophy, used in ACI 318.
And that was in just one number, right?
Correct. That's what's so clever about it. Its value depends on the expected mode of failure. For a beam section where the steel yields generously before the concrete crushes, a ductile tension-controlled failure ACS high, typically 0.90. We have confidence in that behavior.
But if failure is expected to be brittle,
then II drops significantly. For example, for a column where the concrete might crush suddenly, a compression-controlled failure is lower, maybe a 0.65 or 0.75, depending on the type of ties or spirals used. This reflects the lower reliability and lack of warning associated with brittle failures. The phi factor directly encodes the desired level of safety based on ductility.
Wow. Okay, so a phi is like a codified safety margin adjusted for failure type.
Yeah.
What about the basic material properties themselves?
Phi.
The specified compressive strength of the concrete, usually at 28 days. Keyword, specified. It's the target value used in design, not necessarily the slightly higher average strength you might get in field tests. All the code equations are based on this specified phi value. Similarly, phi values is the specified yield strength of the non-pre-stressed reinforcement, the rebar. Again, it's the nominal value used for design calculations related to steel yielding.
Okay. And sometimes concrete isn't standard weight. There's a factor for lightweight concrete, lambda. Yes, lambda is a modification factor used specifically when you're dealing with lightweight aggregate concrete.
Why is it needed?
Because lightweight concrete, even if it achieves the same compressive strength as normal weight concrete, generally has lower tensile strength and is more brittle. Its modulus of rupture and splitting tensile strength are lower.
So lambda adjusts for that.
Exactly. For normal weight concrete, lambda is $1. For lightweight concrete, lambda is less than 1.0, maybe 0.85 or 0.75, depending on the type. This factor gets multiplied into various code equations, particularly those related to shear strength or development length, effectively reducing the calculated tensile capacity to account for the aggregate properties.
So if an engineer designs with lightweight concrete, but forgets to apply the correct lambda factor,
they'd be overestimating the concrete's tensile strength and potentially its stiffness, which could lead to unexpected cracking, excessive deflections, or even shear issues. It's a critical adjustment factor.
Underscores the need for precision with these notations. What about strains? You mentioned epsilon.
Epsilon is the net tensile strain in the extreme layer of longitudinal tension steel at the point of nominal strength.
That sounds technical. Why is it so important?
Because its value is what formally determines whether a flexural member, like a beam or slab, is tension-controlled, compression-controlled, or in the transition zone between them.
And that classification dictates the several factor we just talked about.
Precisely. If epsilon is large, meaning the steel has yielded significantly, it's tension-controlled, $5.90. If epsilon is very small or compressive, it's compression-controlled, $5.655 or 75 cents. If it's in between, SELA varies linearly. So calculating epsilon is the key step in determining the correct strength reduction factor, which is fundamental to safety. It's the mathematical measure of ductility.
Okay. And one last one for serviceability, EPSA, the modulus of elasticity of concrete.
This represents the stiffness of the concrete, how much it deforms under stress. It's crucial for calculating deflections, vibrations, and for understanding how loads get distributed in indeterminate structures.
Is it just a fixed value?
No, that's the key. AVL depends on both the concrete's compressive strength and its density, related to whether it's normal weight or lightweight captured by Pockish. Chapter 19 provides the specific empirical equation mandated by the code for calculating LRE based on these properties.
So you can't just pull a generic L-Arcus value from a textbook.
You shouldn't. You need to calculate it using the code's formula based on the actual specified $5 in density for your project. Using the wrong LR means your deflection calculations will be off, potentially leading to serviceability problems like excessive cracking or bouncy floors, even if the member has enough strength. Chapter 2 ensures everyone is using the same agreed-upon basis for these fundamental properties.
It's crystal clear then. Chapter 2 isn't just definitions. It's the mandatory alphabet and grammar for writing the structural design equations in the rest of the code. Without mastering this notation, the calculations are impossible or, worse, incorrect.
Absolutely. You need that common language.
Okay, let's wrap up our deep dive into Chapter 1 with that essential peek into Chapter 2. What are the main takeaways?
Well, I think the biggest thing is reinforcing that Chapter 1 is the non-negotiable legal and procedural starting point. You have to grasp the code versus commentary distinction. Code is law, commentary is guidance.
Right. And that critical line between the engineer's design responsibility and the contractor's means and methods.
Huge for liability. And knowing the specific applicability boundaries, where does 318 apply? And just as importantly, where does it explicitly not apply? Remembering the 10-inch pile rule, the residential carve-out, when to jump to ACI 350 for tanks or ACI 440 for FRP.
Those exclusions are really practical guardrails.
They prevent misapplication of the code. And finally, understanding the roles the BO enforces, the LDP designs, and holds ultimate responsibility, even with delegation. Chapter 1 maps out that whole ecosystem.
And we established throughout that ACI 318 sets the minimum bar for safety, durability, integrity.
The absolute minimum.
But engineering isn't just about meeting minimums. It's often about achieving specific project goals, longevity, performance.
Which leads perfectly into our final thought for you, the listener. We know the code mandates minimum requirements, but think about the pressures beyond basic safety today. What about things like the increasing cost of future repairs due to more extreme weather from climate change? Or the growing demand for structures with a much lower embodied carbon footprint over their entire, maybe 100-year service life?
So factors beyond immediate code compliance.
Right. What specific economic or environmental drivers might push a thoughtful licensed design professional to voluntarily design beyond the ACI 318 minimums? Maybe specifying significantly more concrete cover for corrosion protection, or demanding concrete mixes with lower cement content, even if it means higher initial costs.
To guarantee much better long-term resilience or sustainability.
Exactly. Where does the engineer's professional duty potentially shift from just meeting today's minimum code to making strategic choices for a much more uncertain and demanding future? Something to think about.